Okay. The next question, sketch the surface. Okay, so this is a Greek letter called psi. Okay, psi. This is a capital form of psi. The small letter form of psi is I believe it's like this. Yeah, kind of resembles an E, but let me write that better. Okay, so this is small letter psi, and then this is a capital letter psi. Okay, so sketch the surface psi given by this equation, and it is bounded between z equals to 1 to z equals to 4. Evaluate a suitable surface integral to compute the area of psi. Okay, so let us sketch how this looks like. So take a look at this. You notice that this is the form of a circle. Okay, the in 2D space, okay, in the xy coordinate system, the equation of a circle is given by x squared plus y squared is equal to r squared, where r is the radius of the circle, right? So you know that this will look like this on the xy plane, like that, and this has a radius of r. Okay, but how are you going to do this in 3D space, right? Now we have the z coordinate to take care of also. So how it looks like is this. So let us consider the two extreme values of z. The first case is z is equal to 1, right? So we substitute z equals to 1 into here. Okay? So there. So this is actually a circle of radius 1. Okay? So on one extreme, we have a circle of radius 1. Then what about the other extreme? The other end says z is equals to 4. So we will substitute z equals to 4 here. So this is a 2 squared. Right? 4 is actually just 2 squared. So this is a circle of radius 2. Okay? So if you want to sketch this, so now this is my x, y, and z axis. Then, okay, so let's take a look. At z equals to 1, so somewhere on the z axis at z equals to 1, we have a circle of radius 1, right? So let us sketch out a circle. Okay, so notice that this circle is parallel to the what do you call this? The xy. The circle is parallel to the xy plane. Okay, the circle is parallel to the xy plane. Now, what about the other extreme when z is equal to 4? Okay, at z equals to 4, we have a circle of radius 2. Okay, so let's go to z equals to 4. And then on z equals to 4, we will draw a circle of radius 2. So it should be a bit of a larger circle. Okay, all right. So yeah, then in between, right, we shall connect them like this. Okay, with a curve. Okay, so actually this is approximate, but yeah, since this is a sketch, this is approximate. But if you want to know why it's a curve, it's because okay, look at the general form of the surface. It's like this, right? Z. Then I can change this by saying Z is actually Z square root it and then square it. Okay, so I didn't change it by square rooting and square root. So you see that this takes the form of the circle equation, right? Where the radius is given by square root of Z. Okay, so as you vary along Z, the radius of the circle will vary square rootly. Okay, the radius of the circle will vary square rootly, which takes the form of this curve. Okay, yeah. So this is the sketch of the curve psi. Okay, so the name of this curve is psi, which they told us. Okay, what do they want? They want us to calculate the surface area of this integral. Oh, sorry. They want us to calculate the surface area of psi. Okay, so to do that, we need to know we need to know how to calculate surface integrals. So, let me show you how to calculate the steps to calculate surface integrals. So how to calculate. Okay, So surface integrals is denoted like this. Okay? So this is a surface integral. Okay? So this is a surface integral. Then this is given by the formula. Okay? It can be simplified by taking so it's quite long, so bear with me. Okay. So what the heck is this formula telling us? What it's trying to say that if you are given a surface, okay, let's plot out a random surface. So suppose we have this surface here. Okay, so this is a surface S. Okay, that's what this S is referring to. It's referring to the name of the surface. Okay, we want to perform the surface integral with this function. Okay, so what is d sigma? D sigma is an infinitesimal area of this surface S. So if I cut up this surface S into many small pieces, right? So I cut it all into many small pieces. Each of this little piece right here, okay, each of those little piece right here is called d sigma. Okay, so that's what d sigma refers to. It refers to the infinitesimal uh an infinitesimal portion of the surface S. Okay, so this is S, and d sigma is an infinitesimal portion of it. Okay, so d sigma is given by this formula here. Okay, so square root of 1 plus z x squared plus zy squared dA. Okay, so you can find this formula in the formula sheet of the final paper, but my notation is slightly different. Okay, my notation is slightly different. So what is zx here? Zx here refers to partial z partial x, and zy here refers to partial z partial y. Okay, so that's just my notation. And then you notice that the g functions are also different. So the only difference in this g function is the z, right? So let's take a look at what is going on in the z. What is going on in the z is that this z becomes z of x and y, meaning that z has become a function of x and y. In other words, z, right, will be expressed in terms of x and in terms of y. Okay, so this may not be clear to you right now, but when we go to an example, I will re-emphasize what this means. Okay, so let's go ahead and look at the steps of how to calculate a surface integral. Number one, you make z. Okay, let me just write this down first. Okay. So let's start from step one. Step one makes Z the subject of the surface equation. So what am I talking about? So this equation, right? Sorry, this surface that I show you here is given by some equation. Okay, it's given by some equation. For example, in this question, right, the equation of the surface is here. Okay, so we need to make Z the subject of the surface equation. It's just nice that in this question, Z is already the subject of the surface equation. So we do not need to do the first step. Sometimes it may not be the case. Okay. For example, I give you a flat surface, like for example, x plus y plus z is equal to 10. Okay. So I need to rearrange this equation such that z will become the surface subject of the equation. Okay. Z will become the subject of the equation. Okay. But in this case, we don't need to because z is already the subject. Okay, now let's move to step two. Step two says sub z into g of x of y of g of x, y, z. Okay, so um, yeah, so we have this function that we need to integrate over the surface. Okay, let's just say, as a very simple example, g is given by x plus y plus z squared. Okay, the z that I obtained from here, right? The z that I obtained from here, I need to substitute it into here. Okay, I need to substitute it into here. So that means this equation will become purely a function of x and y. Okay, plus this x da 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 y da da da. Okay, meaning to say, okay, what do I mean by purely a function of x and y? Meaning to say that this g, you will now see x and y only. You don't see z appear. Okay, you only see it in terms of x and y, and z will not appear in the function g. Okay, so that's what I mean here. So this one here, purely a function of x and y. Okay, next, we need to evaluate d sigma. Okay, d sigma is the infinitesimal portion of the surface. And it is given by this formula, which I will not derive, but just use this result as it is. Okay, so zx is the partial derivative of z with respect to x. This z here is from the step one. Okay, this is from step one. Okay, where we make z the subject of the surface equation. And same with here too. Okay, so you partially differentiate z with respect to x with respect to y, and then you plug it into this to obtain d sigma. Okay. Next step is you will perform the surface integral. Okay. So having found this, okay, we already found this in step 3, and we already found this in step 2. Then finally we can do this surface integral. Okay. So don't worry about this. I'll show you some examples of how this would look like. So a reminder in step 4 is that sometimes you need to convert it to suitable coordinate system. Okay, so what do I mean by suitable coordinate system? So normally we would do it in x and y coordinate, x, y, z coordinate system, right? But then sometimes if you're involving circles, it might be better to use polar coordinate systems. Okay, that way it will make the integrals much simpler. Then uh, another note to take is that you need to identify the bounds of the integral, right? Because you're doing integration, you're doing proper integration, meaning that your integration has limits, okay? You know, like this and this. You need to identify them, right? So how do we identify them? We identify it from R, okay? So what is R? Okay, so notice in the formula here, we have this here which says S. Then down here it says R. So what is R? R is the region of S projected onto the XY plane. Okay, that sounds very sophisticated, right? But what does that simply mean? Okay, so take a look at the surface S here. Okay, I'm gonna redraw S down here. So what this means is that, okay, suppose we have our X, Y, Z axis, then we have our surface S. Okay, yeah, we have a surface S. Okay, R is this. Okay, so this one is S, right? Then let me draw some straight vertical lines down onto the XY plane. Okay, yeah. So you see on the XY plane, right, we have this rectangle. This is the region that we call R. Okay, so this region is called R. So R stands for region. Okay, so let me say that again. Technically speaking, R is defined to be the region that is projected. So it is the projection of S onto the XY plane. Okay, so let me say that again. R is the projection of S on the XY plane. Okay, so what does it mean? It's quite abstract, right? So I want you to think about it like this. Think of S as an opaque sheet of paper, okay? Some opaque sheet of material, okay? Then I want you to think that from the ceiling, right? Okay, so from, let me rub this away. So here's the ceiling, and the XY plane, we take it to be the floor, okay? So imagine from the ceiling, right? All from above the ceiling, there will be light rays shining downwards, okay? Light rays shining downwards. All points from the ceiling, there are light rays going downwards onto the floor, okay? That vertically downwards. So as they go down, some of them will be, some of them will reach the floor, right? Some of them will reach the floor, while some of them will be blocked by the opaque sheet that is S, right? Some of them will be blocked by this sheet that is S, okay? And then some of them here will go to the floor, will reach the floor as well. Okay, so you see, since it is blocked by the surface S, right? So reminder here, this is the surface S, which we think to be opaque. Since it is blocked by the surface S, there is a region below S which will cast a shadow, right? Which will cast a shadow onto the floor. Okay, that shadow, you can think of it as the region R. Okay, so that is what I mean by R is the projection of S on the XY plane. Okay, so to explain it in layman terms, you think of it like this. Imagine there are light rays from all points of the ceiling shining downwards onto the XY plane, okay, which is where we take it to be the floor in this case. Okay, some of them will reach the floor, some of them will be blocked by the surface S. Okay, then because it is blocked by the surface S, S will cast a shadow beneath itself. That shadow, the exact shape that it forms on the XY plane, is called R. Okay, it is called the projection of S onto the XY plane. Okay, so now I hope you have a solid understanding of what R is and what S is. Okay, good. So let's go and continue with this. Yeah. Okay, so now we can do this scratch. Okay, so I already sketched it out here. So that's the first part of sketching the curve. So now I'm gonna teach you how to do the calculate the surface area. So for 3D surfaces, right? To calculate the surface area, so surface area, it is given by this formula. V sigma, like that. Okay, so you notice that there's no G here, right? G of X, Y, Z. Right? There is no G here. Okay, so it's just like the surface integral formula, except there's no G here. Okay, so how can we make sense of this formula? Okay, to make sense of this formula, remember what I said, that d sigma is infinitesimal portion of the surface, right? So let me just give you a flat sheet surface, which is easier to visualize. So this is S. Yeah. Then if we cut it up into infinitesimal portions, each of these little tiles is called d sigma. Okay. And then remember in one of the earlier, one of the, I think in one of the previous class, we stated that integrals means a continuous sum. Okay, integrals means a continuous sum. Okay, so by continuously adding all these little tiles up together, these little infinitesimal portions together, when you add them all up, they will form the surface area, right? If you add up all these little tiny areas, eventually they will form the entire surface area of this surface, of the surface S. Okay, so that is the logic behind this formula, double integral d sigma. Okay, that is how you use this formula to calculate surface area of a surface, okay, of a 3D surface. Okay, so Okay, let me quickly sketch that out again. Okay, so that's our surface. What we need to do, we need to evaluate the surface. So we choose the formula. What we need to do next is okay, I want you to take note that this is a radius of 2. This one has a radius of 1. Okay, so first step, okay, make z the subject of the surface equation. It already is, right? Z is equal to x squared plus y squared. Okay, the next step is what? Let's take a look at this. Next step is sub z into the g of x or y. In this case, we have no g, so we don't need to do that. Then what's the following step? The following stays to evaluate d sigma. Okay, so let's take a look. D sigma is given by the formula. Okay, where zx is given by the partial derivative of z with respect to x. So in this case, I'm referring to this z here. Then if you evaluate this, it will be 2x. Okay, do the same thing, but now with respect to y. Okay, so we have zx, zy. Okay, so we're going to substitute these results into the d sigma formula. D sigma is equal to, so this squared plus this squared dA is equal to, okay, yeah. So after finding d sigma, what is our next step? Our next step is to perform the surface integral. Okay, so we have all the ingredients we need now. So remember, we are finding this, right? This is our surface area S. Then, okay, now replace d sigma with this, which is okay. So let us identify how the region R looks like based on our sketch. So remember what I said. In order to imagine R, you cast light rays from the ceiling down onto your surface. Okay, so there are many light rays from the ceiling down onto your surface. Then some light rays will reach the floor, while this opaque sheet of your surface will block the light. Okay, so let's say, see, the light coming down from here will be blocked by the sheet, so it cannot pass through. The light coming down from here will be blocked by the sheet, so it cannot pass through. Okay, blocked by the sheet, cannot pass through. Blocked by the sheet, cannot pass through. But then you see, this circle of radius 1, right, is a hole. Okay, is a hole. So that means it will let light pass through that hole. Okay, so light will pass through, and light will continue to pass through. Okay, light will continue to pass through until it reaches the other side of the sheet. So again, it cannot pass through. Then again, it cannot pass through. Okay, then on the other side, on the outside of the surface, it will pass through again. Okay, so notice that it will form a shadow, right? This surface will form a shadow, and the shadow looks like this. Okay, so this is light going through the hole of radius 1, and then here there is a shadow that is formed by the circle of radius 2. Okay, so in the end, your region R looks like a donut. Okay, basically it's a concentric circle. Okay, so this concentric circle is the region R. So it looks like a donut. Okay, so if this is very hard for you to visualize, don't worry, I've made this on SolidWorks for you to visualize this. So let us take a look at my SolidWorks. Okay, so here in SolidWorks, I roughly sketched out the surface facade to help you visualize what is going on. Okay, so this should look like the surface that I sketched out. Now, how can we imagine the what do you call this? The shadow, the projection R onto the XY plane? So now I made it transparent, right? But now I'm gonna make it opaque. So I'm gonna make it opaque. Okay. So yeah, it continues to look like that. So you see down here, that is the radius, that is a circle of radius 1, right? That occurs at z is equals to 1. And then at z equals to 4, this bigger circle here, this bigger circle is of radius 2, okay, which occurs at z is equal to 4. Okay, so how do we visualize the shadow R? So what I'm gonna do is I'm gonna go into to here, right? So you see this top plane is referring to the XY plane that we were talking about just now, which I call the floor. Okay, so I'm gonna click on the top plane. Then what I'm gonna do is I'm gonna sketch on the, sorry, I'm gonna click on the top plane. Then I'm gonna use the circle sketch. Then you see the light can pass through and reach the the floor through this hole and the outside of this surface. So what I'm gonna do is I'm gonna trace this hole, and then I'm gonna trace the outer edge of the surface. Okay, perfect. Click OK. Then, okay, now what I'm gonna do is I'm gonna tilt it and check the XY plane. So let's take a look. Ta-da! Do you see that this XY plane will project this shadow R? Okay, it will project this shadow R. So that's what I'm talking about. All the light rays can go through the outside here and go through the inner circle here. Okay, leaving behind only this little tiny uh concentric disc, okay, which is a donut. Okay, so now I'm gonna go back to my OneNote. Yeah, okay. So since the region R is circular, right? So really, since the region R is circular, we need to convert this to polar coordinate system. Okay, it's more appropriate to convert this to polar coordinate system. Okay, so convert to polar coordinates. Okay, so you must remember in polar coordinate system, x squared plus y squared is equal to r squared. Okay, this basically comes from Pythagoras theorem. Then x is equal to r cos theta. Then, sorry, y is equal to r sine theta. Okay, so these are three important relations that you can find in the polar coordinate system. Okay, the polar coordinate system. Okay, and the reason why I do this up, just for your side note, is because r is circular. Okay, so what else do we need to know? Okay, we also need to convert this dA into the polar coordinate system. And in the polar coordinate system, right, dA is given by r dr d theta. Or you can also swap them around. So you can say r d theta dr. Okay, it doesn't matter. Okay, so now let us do some modifications. Okay, let's do some modification. So what I'm gonna do is I'm gonna copy this and then convert this into polar coordinate system. Okay, so what am I gonna do? Inside here, right, I'm gonna factorize 4 from these two terms. So when I factorize 4, it becomes like this. Why do I factorize 4? Because I will obtain x squared plus y squared. Do you remember? In polar coordinate system, x squared plus y squared is equal to r squared. So I'm going to replace that with r squared. So this is r squared. And this dA, I'm going to replace it with r dr d theta. Okay, so yeah, now we have to find the bounds of the integral. So the inner integral is r. Okay, so r equals to something, and r equals to something, and then the next integral is theta. So theta equals to something, theta equals to something. So let us take a look at the theta bounds. Okay, so remember that our region R is this one, right? So let us focus on the XY plane only. Okay, so let's sketch the XY plane and let us draw the region R. x, y. Okay, so the region R is given by this donut. Wait, the proper mathematical name of this donut is called an annulus. Okay, annulus. Uh, and what am I doing here? What I'm doing here is basically I'm viewing this donut from the top down. Okay, I'm looking downwards. Okay, so this is my eye, and I'm looking downwards into the donut. Okay, so I hope you understand what I'm doing here. Yeah. Okay, so let's see how the radius varies in this donut. Okay, so the radius starts from here, r equals to 1, right? So remember the first radius is r equals to 1, and then the outer radius is r equals to 2. Okay, so now we know the radius is bound between r equals to 1, r equals to 2. What about theta? Because this sweeps one round of a circle, right? One round of a complete circle, it will start from 0 and then end at 2 pi. Okay, so yeah, you can do this integral using your calculator, but I think it's quite simple. You can do this by hand. So let us do this by hand very quickly. Let's use substitution. So let u equals to 1 plus 4r squared. Differentiate this with respect to r. This will become 8r. Then we need to make r dr the subject. So bring dr to this side, bring 8 to this side. So we have du over 8 is equal to r dr. So wherever I see r dr, I'm going to replace it with du over 8. Okay, so this one I'm going to replace it du over 8. And then since we let the inside here become u already, replace it with u. And don't forget, since we express this in terms of u, right, we need to change this bounds also in terms of u. So let's take a look at the lower bound. So when r equals to 1, okay, we use this expression here, u equals to 1 plus 4 times 1 squared. This is 5. Then the next bound is when r equals to 2, u equals to 1 plus 4 times 2 squared, which is 4 times 4, 16. 16 plus 1 is 17. Okay, so that's the upper bound. Okay, so 0 to 2 pi. Then this one is 5 to 17. Right, now this is in terms of u instead of r. Then this one is u to the half, then times du over 8. Right, so instead of du over 8, I'm going to write 1 over 8 du d theta. Okay, so this 1 over 8, I'm going to pull it outside. Then this one, it would become power plus 1 divided by new power. And then you put in the integral limit, which is this. Right? And then 2 and 8 can cancel, give me 4. Then 4 times 3 is 12. And then this I can substitute in 17, 3 over 2 minus 5, 3 over 2. Yeah, then we do this integral. Right? So let me do this integral at the side. So integrating 1 will become theta. Then you put in the limits, this 2 pi minus 0 over 2 pi. Right? So we replace this with 2 pi. It becomes half 17, 3 over 2 minus 5 over 3 over 2 times 2 pi. And then if you just put this all in your calculator, it becomes 30.84. And this matches the lecturer's solution. So the lecturer's solution is very funky answer, which is this. I mean, mine is also kind of funky. But it's the same thing. So if you put it in a calculator, it's also 30.84. Okay, so that's how you do the this surface integral question, right? Yeah.